My screen is visible, right?
Yes, sir.
Okay. So today we will just start with the essentials of thermodynamics in the metamorphic system. So I think uh, in a class, I think in which you guys were absent. Have you seen the recording of the chemical thermodynamics class?
ये सर हमारा थर्ड इंटरेक्शन क्लास था उस क्लास में हम लोग ऑप्शन थे
Okay. One second. One second. Hello. Hmm. হুম। না দাদা, আমাদের তো ক্লাস ছিল সেকেন্ড হাফে, তাই যাওয়া হয়নি। আহ, ঠিক আছে, কালকে সকালে আমি গিয়ে জিজ্ঞাসা করবো, আমি সকাল সকাল চলে যাবো। হুম হুম, ঠিক আছে, আমি সকালে গিয়ে একবার জিজ্ঞাসা করবো। Yeah, so have you all seen that video of chemical thermodynamics?
वो सर हमारा सेमिस्टर चल रहा था
Okay,
इसलिए थोड़ा
okay. So it's not a very big deal. So because in that chemical thermodynamics part, I have covered the Gibbs Duhem equation and how chemical thermodynamics is important to understand the metamorphic reactions. I have shown the derivation of the Duhem equations, and uh, I have just covered the basics of chemical thermodynamics. But it's not a problem at all, because in today's class I thought of having covered the thermodynamics, the essentials of thermodynamic systems, which we basically use in the metamorphic system. And I think uh, these are the terms like entropy, Gibbs free energy. You must have uh, come up with the terms, right? Because these are the terms which you have all read in your class 12 textbooks, right?
ये सर
Yes. So basically, uh, the motivation of today's lecture is that how we can integrately approach our understanding of the thermodynamic systems, and how we can incorporate this understanding of our thermodynamic system into the real world scenario in the geological systems, right? So we will just see the applications of thermodynamic system, how we use thermodynamics in order to understand the chemistry and physics of natural systems in rock forming minerals, or in the let's say in the rocks, or in the uh, deeper part of the earth. Okay. So uh, and in order to do that, we will look at the entropy first, because entropy is a very important term. Entropy and Gibbs free energy, this you all know basically the definitions. And we will lastly we will see the Clausius equation, uh, because once we can understand what are the function of entropy and Gibbs free energy, the rest will fall into its place. Okay. So now we know that rocks in the mantle melts, right? The rocks melts basically, uh, producing magmas. Then again it crystallizes further to form the melts crystallizes further to form rocks. And by the collectively, by the aggregates of minerals, we say a rock has formed, right? Now many these many processes which occur simultaneously in our natural systems, like sediments, or rather detrital sediments, they transform or they metamorphosed to form metamorphic rocks, and so on and so forth. So these all natural processes occur throughout our geological system. Now the question which generally comes to our mind when we are dealing with the natural or geological systems, that what drives these processes, means what are the key or driving factor that actually uh, that tries to do these processes, like, so the science that explains all these things happening in and around our uh, natural system is governed by the study of thermodynamics. Okay. So uh, basically thermodynamics, it deals with the several parameters, and throughout this parameter, the one important aspect is our entropy and gives free energy. Now, so these two are the most important parameter which we will be covering in this topic. Uh, so in this lecture, I will not restrict myself in entropy, but I will be covering the gives free energy part also. But we will deal with the entropy first, because because entropy, when entropy hits our mind, or when we say about entropy, the certain thing that comes to our mind is the randomness of molecules or atoms in a system, right? So do you all understand by randomness? So what actually randomness is? Do you know? Anyone?
सो जो डिसऑर्डर होता है एंट्रोपी होता है जो
Yes,
एक सब्सटेंस
exactly.
में जो डिसऑर्डर होता है.
Yes, exactly. You can say an ordered disordered arrangement. That is what we call, in general sense, that is what we call a randomness. So randomness, generally in geological system, we when we try to explain randomness, we generally consider molecules or atoms of a crystal structure. So before going into the crystal structure, I will just give you a very basic explanation. Just imagine a group of players are playing football in a field, right? So when they are playing football in a field, their energy level is high, and when they are not playing football, the energy level is minimum or low, right? So when the energy level is low, they are sticking to a fixed position, means they are not moving, they are just standing or they are sitting at a particular place, but they are not moving when the energy level is low. So the moment when the game starts or when the ball starts moving, it becomes a zigzag movement or a random movement of the player. So each and every player tries to capture the ball. So what this means the players are moving with a certain sort of energy, and that energy in terms of thermodynamics we call the vibrational energy, right? So when the so basically when everything starts moving, so the energy level is increasing from a certain point to a point, right? It is increasing, and the energy follows, or the vibrational energy, let's say, follows in a random direction, right? So so this movement, so the same thing happens in our inorganic world, right? So suppose there is a crystal lattice. So this is a crystal lattice, right? So in this crystal lattice we can see that sorry, yeah, so in that crystal lattice we can see that there are 8 points or 8 corner, right? So in this 8 corner, some I have marked with this open circle and some with cross. Now so we all know what a crystal lattice is. Crystal lattice is basically a building block of your minerals. So just like a brick in a house, so there are two types of atoms which I have marked. One I have marked with this open circle and one with the cross. So basically, in through this diagram, what I am trying to represent, or what I am trying to tell you, the bigger picture is that these small let's say circles, or these small atoms in the crystal structure, so these are bonded to each other, right? So if you observe this crystal structure, so if you take any one of the cross section, so we will see that this is the basic configuration of the atoms which are structured in a unit cell, right? So these are basically bonded or sticking to one another. But this crystal structure, we what we know as of textbooks, that these are static. They may look like static, but they are not static. Please remember this in mind. In when we study thermodynamics, or when we are about to infer something about the crystal structure, the first boundary condition that we uh, actually, this is not a boundary condition, this is reality, that these are not static. When we are seeing a solid phase, the crystal structure are so intact and their energy level is so low that the vibrational energy uh, actually impinges to a very minimum level. So that's why uh, the solid state or the solid state material are considered to be the most stable one, because their vibrational energy tends to zero, are very very low. But the thing is, they are not static. They actually uh, uh, jumps or vibrates in their positions. Now what happens when we subject these solid state or let's say any state of matter at higher temperature, the vibrational frequency increases at a very greater extent, and the increase and the amount in which they increase, it is so much that uh, under certain condition we may, or during experiment we may see that they are moving at a very greater speed or with a very higher amount of vibrational energy. Now so like just like the football players who are who are playing football in the field. Okay. uh, now so the and the thing is, they vibrate in all and every possible direction, right? They vibrate in every possible direction. So this term we called the entropy. So entropy is basically measure the randomness of any constituent particles in every possible direction. So I will write this exact definition for you. The entropy measures the randomness of any constituent particles in every possible directions. And this possible movement in each and every direction is caused by if external factor you can say, or internal factor, which is this T, temperature. If we increase this temperature, the randomness will increase. Okay, that is, the atom will start jumping or start moving from one place to another. And this type of entropy we generally called as thermal entropy. Okay, so basically entropy are of two types. One is thermal entropy and the other one is configurational entropy. Right. So the entropy, which is so both the entropy are caused by increasing in temperature, but so the thermal entropy is basically are the one which generally increases with the increasing with temperature. And there is, as I have already mentioned, there is another type of entropy which is the configurational entropy. So these are the entropy or which are generated by swapping of positions, right? So this type of entropy is called configurational entropy. Let's say when the players are playing football in the field, so we have seen many times then that the players exchange their positions. So let's say a player is playing, then in substitute of that player another player comes, or sometimes they change their positions. So what it means, what I'm trying to say is they are swapping their positions, right? So this kind of entropy is called configurational entropy. Or we can let's take a very basic example. Let's say uh, this is a cross section of a romb, right? So let's suppose there is an atom here at this place. This is the position X, and let's say in this two-dimensional space we can mark a position Y. Now if this atom, if this atom changes its position or swap its position from this particular position X, and if it changes to this position Y, then there will be a vacant space which will be created at this particular position Y, right? So it means there is a redistribution of this of its position. Now this is a change in the configuration of this particular cross section romb. right? So if this is wrong, so if there are very small circles which are constituting or making up this ROM, now if you suddenly take this open circle and if you swap this position with respect to y, now there will be a distortion in this perfect figure of ROM, right? So the configuration will change, and the entropy which deals with swapping of the position of constituent particles is called your configurational entropy, right? We generally demarcate this configurational entropy with SCF, and thermal entropy with ST, right? So now while jumping, they may jump to a vacant position, and this is how a vacant structure is created, or change in configuration happens. Now our question is how we can calculate this thermal entropy. Okay, now we know that if we are seeing entropy or if we are measuring entropy in a thermodynamic system, then there are some certain boundary conditions that we must consider. So we know that if a system receives, let's say, an amount of heat, right? If a system receives an amount of heat, so, or any amount of energy, what will be the expression that we can represent that amount of energy? So we generally use the term dq. So are you all familiar with the term dq, guys?
Yes, sir.
Yes. So, and because of the entropy which actually persists in a uh, let's say any thermodynamic or metamorphic system, so that entropy can be increased, that change in entropy can be increased by a set of temperature, that is dt, right? So ds of t will be greater than dq by t. So this is the general expression that we all know, which persists in a thermodynamic or any system, right? And we also know that this dq this dq is the amount of energy which a system receives. So this is amount of energy a system receives. Now let's suppose if a system is not supplied with external energy. Okay, uh, yes. Now if a system is not supplied with external energy, so there will be a energy present or available in the system, right? And sometimes we call that energy is called the internal energy, or also in terms of thermodynamics we generally we use the term, we also use the term, a term called dH, which is the enthalpy of the system. Now when we assume this type of conditions, right, or when we want to calculate the dq, the amount of energy which has, or the amount of energy where it means a system receives the certain amount of energy, we represent the term with dq. And when we want to calculate this particular dq value, right, we generally equate with a term called dH, the change in enthalpy. So this dq, sometimes it, we assume it is equivalent to the dH, because when dq is a system that receives, when a system receives a dq amount of energy, then it is equated to dH, that is the enthalpy of a system, right? Now we know uh, that when this dst is greater than dq by t, uh, this is when for irreversible, irreversible, or we call this system called the spontaneous reaction, right? It means if we are assuming a reaction, let's say a reaction A, okay, if it is spontaneous, it means that it is a one directional, where the dst thermal entropy is greater than dq by t, the supply of the uh, energy received divided by its temperature, right? So when the dst, the thermal entropy, is greater than this value, that is called an irreversible or a spontaneous term, right? And it is only possible if a reaction is a unidirectional or one directional process, and this is always for a irreversible process. This process is always restricted to irreversible processes, right? And in case of reversible process, means what do you mean by reversible process? So can you give an example of a reversible process? Anyone? A very basic example which you have learned in class in your class 10 or 12. What will be an example of a reversible process? I am telling you the mathematical expression that dst equals to dq by t, means when the thermal entropy will be equal to that of the dq by dt term, when these two will be equal, it means yours one set of reaction, say a plus b equals to c plus d. So the product and reactant, these two are in equilibrium with each other, means a plus b can satisfy c plus d and vice versa, and from c plus d you can come back to a plus b. This is a reversible process. Okay, so can you give a very basic example, anyone? What will be a reversible example? What will be the example? A very basic.
सर जैसे हम अगर फूड को बर्न कर देंगे तो फिर वो कोल में कन्वर्ट हो जाएगा जो कि फिर से रिवर्सिबल नहीं हो पाएगा.
That's an irreversible reaction, right?
सर इरिवर्सिबल रिवर्सिबल सर वो जो नाइट्रोजन और ऑक्सीजन के कॉम्बिनेशन से नाइट्रस ऑक्साइड फॉर्मेशन होता है वो रिवर्सिबल होता है.
And any more or basic example which comes which is coming to your mind?
सर आइस और वाटर.
Exactly. So ice and water is the very basic, I mean, reversible reaction example. Okay, and we you can also take example in systems, but जैसे कि अगर तुम कोई भी अगर तुम लोग कोई एग्जांपल लेते हो कोई भी सिस्टम का, फॉर एन एग्जांपल इफ यू आर कंसीडरिंग दिस reaction Mg2SiO4 plus SiO2, so it will give you Mg2Si2O6, right? you can you also can take our example of reaction from geological systems, but there is a restriction in this kind of uh, reactions, because when your frosterite is reacting with SiO2, it will give you Mg2Si2O6. Mg2Si2O6 is a pyroxene. It's a formula of enstatite. It may looks very simple, but when you will try to convert the enstatite to olivine or to silicon, it will involve a, a series of steps, right? You have to introduce many more terms. You have to introduce fractional crystallization, fractional melting, equilibrium crystallization, equilibrium melting. Then these are the complications which will arise if you try to uh, uh, incorporate this. But generally with the help of thermodynamics or metamorphic thermodynamics in metamorphic systems or igneous systems, we generally try to decipher this kind of reactions, right? So we will just see what we can do next in this thermodynamics. So from these basic examples and basic concepts, you will get the idea how we actually calculate these reactions of geological systems with the help of thermodynamics. Now I will say a bit about entropy in isolated system, right? So in case of entropy in isolated system, uh, there is one set of boundary condition, that is the system which we are working with does not receive energy from outside or any external source, right? So what I mean to say is, so dq is the amount of energy that is supplied to a system, which I already told earlier, right? So it is the energy available to any kind of system. But listen it very carefully, if a system has been restricted with the flow of any external energy. It means if we are not supplying uh, dq, or means if we are stopping the energy supply, it means dq tends to 0, right? So this dq will tends to 0, and the if d, we know that the dst is greater than dq by t. If dq tends to 0, it means d of st, sorry, will be greater than equals to 0. Right? So it means that uh, the thermal entropy in an isolated system can always increase, it will never decrease, because from this mathematical expression we can see that d of st is always greater than equals to 0 if the system has been cut out with the supply of any external energy. Means if dq is tends to 0, then dst will be greater than equals to 0, right? So it means it can be equal to 0 but it cannot go below 0, it will always be greater than 0. It means the thermal entropy in the isolated system can always increase but cannot decrease. So our objective is to calculate the value. So we know from the simple equation of heat that if H is your heat, we know that H equals to M into S into T, where M is the mass, S is the specific heat of a system, and T is the temperature, right? So, so if I replace this S with Cp, so then Cp is the specific heat capacity at any constant pressure. And if we consider that mass equals to 1, then our equation of heat will be Cp into T, right? Now if we differentiate each side, dH equals to Cp into dt, where dt is a very small change in temperature, right? Now here Cp is related to temperature, which can be estimated by an equation called Mayer-Kelly equation. Okay, so it's nothing to be worry about, that this Cp is our specific heat, right? So this specific heat is actually related to a kind of temperature, and in through this Mayer-Kelly equation we can write that Cp equals to A plus Bt plus C by T square. So this is a specific equation called Mayer-Kelly equation, right? This A, B and C, these are your constant terms, right? These are have values. So it represents that, see, you can actually if you see the specific heat equation from Mayer-Kelly, you can see that with A, uh, there are no temperature variable, but with B there is a single temperature variable, and with C there is a temperature variable of 1 by T square. Okay, so it is a very simple equation given by Mayer-Kelly. So now we can incorporate this in the second law of thermodynamics. Okay, we already know from the previous equation that dq equals to Cp into dt, and because dq is sometimes equal to dh, right? And dq equals to cp dt, it means dh equals to cp dt. Now if we differentiate both sides, we can write this integral. Now we have to set some boundary conditions here. The boundary conditions will be 298 to temperature H0, 298 of H, that is at temperature 298 your H0 will be at 298, and at when T is unknown, that is T is at any temperature, your H0 would be at T, capital T. Okay, so this is the boundary condition. And why we are taking 298? Because if we see most of the publication or most of the authors who have done several experiment, they actually done their experiment at this particular temperature 298. So for the sake of our calculation, we actually use this limit or the set of boundary condition and nothing else, just for mathematical purpose. Okay, so
हेलो सर, ये जो 290 डिग्री ले रहे हैं वो क्या, वो जो रूम टेम्परेचर को बेसिस पे ले रहे हैं जो 273 और 25 डिग्री सेल्सियस एवरेज रूम टेम्परेचर, इसकी वजह से या फिर कोई और?
yes, it's for the sake of normal condition, normal temperature condition, 273.15 plus और वो प्लस माइनस 25 डिग्री सेल्सियस एट सर्फेशियल कंडीशंस पे. ओके,
ये सर।
if you are doing, let's say, a high temperature experiment, you can suppose you are working at a greater depth, let's say at 3 kilobar pressure, then according to that, generally researchers who are working with high temperature pressure experiment, they set that temperature, but this is the normal temperature condition which we take for the sake of calculation. Matlab, this is a standard value, right? So you know at this particular 298 what will be your uh, particular value, because it's a normal superficial temperature, right? So we can actually match our in-depth experiment with this standardized value, nothing else. Now, so these are the boundary condition, that at 298 Kelvin the H will be of 298, and for unknown temperature the H is H of any T, of any value. Now from the Mayer-Kelly equation we know that Cp equals to A plus Bt plus C by T square. Now integral H naught 298 H naught T Th equals to 298 T A plus Bt plus C by T square dt. Okay, so if we break this limit, upper limit minus lower limit, so this will be an equation. Now this particular equation actually, if you break this equation you will get this form. It's a very simple equation. So this equation tells me if I know the enthalpy of any substance at any temperature. Okay, so if you want to calculate the enthalpy of any substance at any particular temperature, we can just refer to this equation. So if I know the Cp of any equation, specific heat, I can get the enthalpy of any substance at any particular temperature. Okay, so we know that ds equals to dq by d. It is a reversible process, or ds equals to dh by t, where dh equals to cp into dt. Can I write this?
Yes, sir.
Okay. So we will just substitute these terms. Okay. That is ds equals to cp by t dt. So by integration on both sides, we will get integration of ds equals to integration of cp by t, sorry, dt, right? Now here we can say that at t equals to 0, s equals to s0, right? And t equals to t, s will be st. Now if we apply this thing, so st in replace of ds, we can write at t equals to 0 and equals to integration 0 to t cp by t dt plus and s0. I can write this term. So this is the equation that we can refer to from the irreversible, or sorry, reversible process. So, and we also know one thing, that from the third law of thermodynamics, we know that the thermal entropy of any substance is zero at absolute zero temperature. Please do remember this in mind. If you want to calculate the thermal entropy of a substance, and for an absolute zero temperature, okay, at 0 Kelvin temperature, absolute zero means 0 Kelvin, okay, the entropy will be zero. Okay, so this equation tells us that we can calculate the thermal entropy of any substance provided specific heat Cp of that substance. So in the uh, initial initially when I have started the class, I have already told you that we see the atomic structure or atomic arrangements, we think that the structure is stable, but the structure is not stable, because as long as your particular substance or that thing is present in the room temperature, which will correspond to a temperature of 298.15 Kelvin. So it is not an absolute zero temperature. So the entropy cannot be a complete zero. It will tends to zero, tends towards zero. It will be some value towards zero, but it cannot be complete zero. So there will be a movement available to the substance or that systems, right? So so this entropy calculated in this form is the third law entropy, okay, corresponding to the third law of thermodynamics. Now, so these are the a very simple equation that we can calculate. So now we will do the procedure for calculating the configurational entropy. Now what is configurational entropy? So configurational entropy is also a very simple term. I will try to understand this, I will try to make you understand in simple form. Let's say three 9 balls, okay. So this is an unshaded balls, this is shaded, and this is again unshaded. So if they are arranged in this fashion, it means they are in a particular ordered arrangement, right? Or let's say this way. So diagonally they are making an order, or this way uh, they are making an order. So they are ordered in a particular arrangement or particular fashion, right? But sometimes if we again consider the example of players playing in the field, are they arranged uh, during particular position, or during the first 2 3 or the first couple of minutes, let's say, when the players are playing football, they are arranged in certain pattern, right? Midfielder, then your defender, then goalkeeper, then same on the opposite team. But when the game starts, when the referee blows the whistle, they starts moving, uh, running behind the ball, and that time they become disordered, right? So if we see this collection of balls, so this arrangement, so this is a zigzag path, right? So this is a disordered arrangement. So configuration entropy measures how disordered the arrangement is in terms of their swapping position, right? So if I want, I can also place this ball here, but instead of placing it here at this point X, I have placed the ball at the at that point Z, right? So by simple definition, the definition which you did not to remember, which you can uh, absorb it as a concept, that is the configurational entropy measures how disordered the arrangement is in terms of their swapping positions. Please do remember this in mind. I am writing this definition for you guys. Configurational entropy measures how disordered the arrangement is in terms of their swapping positions. By simple definition, this is the proper definition of configurational entropy, and this can be calculated by the expression of SCF is the term through which we mark the configurational entropy, equals to K ln omega, and this K is the Boltzmann constant. So this equation was first given by Boltzmann, so can also K equals to R by 0. I will coming to this term, and this is omega. This omega signifies the
सर सर के क्या आपने लिखा आर बाई
n0. n0 तुम्हारा
जैसे
r,
एवोगाड्रो सर
and r will be your ideal gas. Okay,
यस सर यस
so omega is the number of possible arrangements. Clear? Now what do you mean by omega? K ln omega. Please
सर जो वो एलएन वो क्या है
huh?
जो एलएन एलएन लिखा है आपने
Natural logarithm.
ये सॉरी सर एल ए सर क्या उसमें एल एन या फिर एल एन लिखा है थोड़ा फिर से बोलेंगे ये सर सॉरी सर मुझे एल एन दिखा दो
Yes, yes. This is the natural logarithm. Nothing to be. This is also a very. This equations looks like a bit your difficult equation, but this is very simple equation. Now you have to just understand the term what this omega signifies, because in case of configurational entropy, because you already know that Boltzmann is a constant term, ln is the natural logarithm, but the main factor here is that your omega term. Why we are writing this omega term? What this term basically signify here in this particular equation, in the equation of configurational entropy, the sigma actually, it tells or it calculates at how many possible ways a thing can arrange itself in a given slot. If let's say if there are 20 slots, and if in that 20 or let's say 30 slots, and if at that 30 slots if you have to arrange a ball, then what are the, or if you have to arrange some two, let's say take three balls, okay, and you have to, a task has been given to all of you that please arrange three balls in 30 slots. So if there are 20 students in a class, so 20 students may ask, sir, what is the possible combination that we can arrange that those three balls in 30 slots. So there will be n number of combinations, right? So that is what uh, gives your omega, right? So basically omega is nothing but it calculates, or it's basically calculates the number of how many possible ways or combination the thing can arrange itself in a given slot. Simply it is a problem of permutation and combination, nothing else, right? So we will take a geological example. Let's take potash feldspar. It has three polymorphs, right? Chemical formula is KAlSi3O8. So do you guys agree or not with me? Microclean, orthoclase,
Yes, sir.
and cyanidine, right?
Yes, sir.
Okay. Now, uh, we know that. So, according to this chemical formula, can you tell me what are the number of tetrahedral sites, or how many tetrahedral sites are available to a potash feldspar? Yeah. Hello. Am I audible?
Yes, sir.
Okay. So, how many tetrahedral sites are available in case of a potash feldspar? You can give it a try. So, uh, I think it's not that hard. Uh, Potash feldspar have four tetrahedral sites, right? Mm. Correct me if I am wrong. So three silicon and one aluminium, right? Now, what I'm trying to convey through this example is, so let's draw three sides, four sides, sorry. So these are four tetrahedral sides. IV. One, two, three, four. Four. Yes. So for microclean, these first three sites, this one, two, and three, okay, there will be SI in the first three sites, and here will be aluminium for microclean. So it means if I want to use that this configurational entropy, it will be K ln of omega. So this aluminium will get try to incorporate in this side, okay. So if you want also, you cannot make this aluminium to go in this or this or this side, okay. So this aluminium will be restrict and it will incorporate into this one particular site, so which is fixed. So the site number for this, let's say, is 1, okay. So this aluminum can enter only this site, this particular one site. So here the ln is ln of omega, omega equals to 1, okay. So the SCF equals to K, Boltzmann constant, ln 1 equals to SCF equals to 0, a very less value. The configurational entropy value for cyanidine is, for SCF, entropy will be 0. So sorry, for microclean, we are doing it for microclean, it will be 0. Now in case of cyanidine, if we are taking, let's say we are taking 1 mole of KAl, Si3O8 sanidine composition. Sanidine. It's so now for 1 mole, if you want to calculate the number of atoms, you will multiply it with the Avogadro number 6.022 into 10 to the power 23. And now in sanidine, let's say there are silicon and aluminum uh, elements, silicon and aluminum, but they can swap their interchange their positions. Okay, so 1 mole of, you can take KAlSi3O8. So there will be 1 mole of aluminum and 3 moles of silicon will be present, right, in the sanidine. Now if we want to configurational entropy number, it is a number, it is a particular value, right, K, Boltzmann constant ln of omega. Now in order to calculate the omega here, we need to do a combination. Because why we can do a combination? Because here we have to consider the number of possible ways in which they can swap their position. Here the position is not fixed. It can, among these four, it can go into any of these. Okay, the aluminum can enter any of these. Now this is a condition, so the omega will not be 1 here. So it will be 4 n naught. N naught is our Avogadro number, we know.
सर,
Yes.
माइक्रोक्लाइन में एल्यूमिनियम एक फिक्स है, लेकिन सानिडाइन में एल्यूमिनियम एक फिक्स नहीं है।
Can you repeat the question please?
माइक्रोक्लाइन में एल्यूमिनियम एक फिक्स है, लेकिन सानिडाइन में एल्यूमिनियम एक फिक्स नहीं है।
नो।
ठीक है।
इसका रीजन है, मतलब I will tell you the reason. Let me show this calculation for the configurational entropy. It's a very interesting question. मतलब क्यों फिक्स नहीं है, you will just get to know about this. So देखो, तो this is the process of combination. So हम लोग जब क्लास 12 में मैथ्स करते थे, when we are for doing elementary class 12 level mathematics, we know what is the formula for combination. N0 is nothing but the your Avogadro number. So we, क्या हम लोग क्या करते थे, like for factorial, sorry, 4 factorial, then 4 minus 3 factorial, and again 3 factorial, right? So this is, ये हम लोग करते थे. So this is the term, like for 4C3 NCR n factorial, uh, uh, n minus r factorial and r factorial. So this was the formula which we used to do in our class 12 classes. Now this will give the value of omega. So क्या होगा for sanidine, इसके आगे एक ln है, log है. So it will be k, your Boltzmann constant ln 4 n0 minus ln n0 factorial minus ln 3 n0 factorial, right? So uh, there is an approximation in mathematics or mathematical thermodynamics, that is ln of n factorial equals to n of ln into n minus n. This approximation is called, ये completely एक empirical है, ठीक है, mathematical. You have to remember this. This is called Starling's approximation.
लेकिन सर जो आपने ये जो कॉम्बिनेशन यूज करके जो फॉर्मूला निकाला, इसको भी सिंपलीफाई करके तो इससे भी वैल्यू निकाल के प्रूव कर सकते हैं ना?
हाँ, इसको सिंपलीफाई करके वैल्यू निकाल के प्रूफ कर सकते हो, लेकिन हम लोग ये इस टाइप, ड्यू टू इस टाइप के प्रॉब्लम के लिए, थर्मोडायनेमिक्स के लिए, हम ये अप्रोक्सीमेशन यूज करते हैं जब हम लोगों के पास ln ऑफ n फैक्टोरियल हो जाता है ना. ओके, क्योंकि देखो यहाँ पे ये क्या था, सी दिस इज ln ऑफ ओमेगा. इफ योर ओमेगा इज 4 नॉट फैक्टोरियल दिस, अगर तुम इस पे ln लगाओगे, सो क्या होगा, ln ऑफ 4 n नॉट फैक्टोरियल माइनस ऑफ ln m by n था, तो ln m माइनस ln n हो जाएगा. ये टोटल इन नॉट टर्म और ये पूरा टर्म आएगा, राइट?
Yes, sir.
So when you will expand this, to expand this kind of term, ln 4 n naught factorial, we generally refer to this in this form. This form ln n factorial is the Starling's approximation. Okay. So for S of sanidine k, हम लोग में एन नॉट सब में है कि एन नॉट तुम एक कॉमन बाहर निकाल सकते हो, क्योंकि ये तो फोर एन नॉट एल एन फोर एन नॉट आएगा, ठीक है? तो एन नॉट को तुम कॉमन लेके निकाल सकते हो बिकॉज इट इज द एवोगाड्रो टर्म। सो फोर एल एन फोर माइनस थ्री एल एन थ्री, सॉरी हाँ, यहाँ और यहाँ पे हियर आल्सो देयर वाज वन एन नॉट, राइट? सो दिस एन नॉट को तुम अगर निकाल लोगे, सो दिस एन नॉट विल, एन नॉट इज कॉमन, so it means ln of 1 and ln of 1 is 0, so that is why I have obliterated that term already. Now k of a naught equals to r of r, that is 8.3134 joule per joule per mole, so okay, so k equals to r by n naught we already knew. So अगर तुम ये वैल्यू को बैठाओगे, so it will give your 18.70 per mole. ये हो गया तुम्हारा एस सैनिडीन के लिए. So the entropy, the value of configurational entropy for sanidine is 18.70 joule per k per mole. Okay. So and for S microclean it is 0. Now एक सीरीज आता है, that is S of sanidine is greater than S of orthoclase is greater than S of microclean. So the value ranges from 18.70 to 0. Okay. So S sanidine का जो value था, is configurational entropy का, it is highest. So if you are getting, let's suppose it could be a thermal entropy, it could be an configurational entropy, but the main fact or the main thing which we are dealing with is the entropy is higher. एस सैनिडीन का एंट्रोपी हायर है, इसका मतलब क्या है? इसका टेम्परेचर हायर है, सो इट हैज गॉट एन हायर टेम्परेचर, राइट? एंड this, from this we can infer that S sanidine, we can find S sanidine in volcanic rocks, because volcanic rocks are subjected to higher temperature. That is the reason S sanidine we found, or we find generally S sanidine at higher temperature. And for this particular reason, that Si and Al in case of S sanidine can swap their positions, they can interchange their positions. So now Sagarika was asking me a question that why we are considering that they are changing their positions, because due to the reason is simple, it is subjected to higher temperature, because the value of configurational entropy of sanidine is 18.70, and in case of S microclean, configurational entropy for microclean is 0. So that is the reason we get this S microclean in a slowly cooled plutonic rock, in quartz grained plutonic rocks, microclean. And sanidine we get in volcanic rocks. The temperature difference. And S orthoclase we get in a variety of rocks in varied temperature ranges. So this is the game of temperature and nothing else. This swapping and all. And from this we can also calculate the cooling history or the cooling rate of a rock, right? So we can summarize it in a very simple term, that the total entropy in a system is the sum of its thermal entropy and its configurational one, right? ये हम लोग कह सकते हैं, we can conclude and or infer at this point that S is equals to S of T plus S of CF, right? The summation of St thermal entropy and the configurational entropy will give you the total entropy present in a system. Here we are referring to the system, means we are dealing with the natural systems here, right? So when t equals to 0, your SCF will be also equal to 0. So when we are subjected to this type of condition, so this type of condition refer to the type of substance where we see these are perfectly crystalline substance. These conditions prevail when the substance is perfectly crystalline. Okay, so these are the summary of this entropy. Now we know, I will come with the Gibbs free energy part, right? So we know that we denote the Gibbs free energy with G equals to H, which is our enthalpy, minus T S. S is the entropy, T is your temperature at PT constants. And this equation of Gibbs free energy we can write when our P and T are constant. So Gibbs free energy is related to the heat content of the system minus the product of temperature and entropy, right? And we also know that this G is inversely proportional to stability. So why I'm saying this, the reason is very particular, and that is when the G decreases, the stability of a substance increases, right? So for every substance likes to stay in the lowest energy condition, right? Because if let's say uh, mm, if you are pressing a ball, a soft ball, so if you are pressing it, it means you are applying a certain amount of pressure to that ball. So the surface of that ball will be downward in correspondence to your pressure, but after a certain time period of time your hand will not be able to hold that ball in that particular position, right? So you will see that the pressure which you were applying before, now the pressure is decreasing a bit and the ball is retaining its original shape, right? So it means when the pressure is decreasing, or let's say in terms of energy, when the energy supplied or the external energy supplied over that ball is decreasing, it's retaining its original shape, and that original shape is the stable form of that ball. So what I'm trying to tell you or convey you is that at minimum energy conditions, the substance is becoming stable. So it means the lower the Gibbs free energy, the higher the stability of a substance. So if the G decreases, the stability of the substance increases. Now, every substance likes to stay in the lowest energy condition, right? So we can say that G equals to minus St plus H. Now, this particular equation will follow the equation of a straight line y equal to mx plus c, where m equals to minus s in negative slope and c equals to h. Okay, so although it's a straight line equation, but it is represented by a negative slope. It generally implies that your Gibbs free energy is inversely proportional to stability. Now, let's take an example of a natural system. Solid converts to liquid, converts to gas. This series continues if the temperature increases, right? If the temperature increases. Now we'll just see a phase diagram. Let's draw a phase diagram. So there are three substances. So if there are three substances, and if we are uh, drawing a GT diagram, gives free energy temperature diagram, then the three substances must have three different slopes, right? So here the steepest slope is seen by this water vapor, because the entropy of the vapor is highest, we all know, because in a vapor phase the molecule present in the vapor phase, it can go randomly in any direction, but it, in case of a solid, it will not be able to do so, right? So the entropy of the vapor will be highest, hence it has a highest slope, as we can see from the diagram. And the least steep slope is shown by solid because it doesn't allow its molecule to move around freely. Now this is the point where the solid and liquid line meets, and this is at T1. So at this point both ice and water will be stable, but the vapor will not be stable, because at this point, if we extend the slope for, this is the slope for vapor, right? And if we extend this uh, slope at this particular point, so here the G value will be higher for vapor, and at that point the G of IW, ice and water, is lower than that of G of vapor. Okay, so see, these have very significant meanings. This diagram, G of I comma W is lesser than G of vapor at this particular point. This point is A, let's suppose. So at point A, the G of V is greater than G of IW. It means due to the increase in gives free energy at that particular point A, GW, GV is not stable. It means at that point A, GV, G of V, vapor, water vapor, cannot exist. But G of W and G of I can exist. That is why at that point is called the ice water conjugation line. Okay, because the G of both the substance are same at that point, and the G of vapor is more, it is not same, it is at a higher value, and higher G means lesser stability. So at that point, water vapor is not stable, it is unstable. And if it is unstable, it cannot exist at that point. Okay. So this is a very significant diagram. And this diagram, so I am telling you more. So, and also one thing, the temperature is changing as you are moving from left to right. The temperature is changing, but the pressure is in an isobaric condition, means the pressure is constant, right? So if the P remains constant so long, the ice and water will be together, so the temperature will be fixed at T1. See, at this point this temperature is fixed. So if we move the cursor vertically or move the pen vertically at this point, so this vertical line reflects a constant temperature. Okay. So because we are very long, for a very long period of time, the temperature is for so very long, so it means that for that particular point the pressure remains constant and the ice and water will be together fixed at the temperature T1. So this is called the freezing point of water and melting point of ice, because they coexist at that particular point. So this is the GT phase diagram of ice, water, and vapor, of the three phases, right? So through this phase diagram, you can actually incorporate any kind of mineral and along with their melts present within the natural system. So exactly you can just able to infer why some solids coexist with melts. Okay, so from this system you can actually able to trail the systematics of the thermodynamic system. Now and for this particular point B, you can see that water and vapor are can be stable here, and at that point the G of ice, so this is the G of ice line, sorry, uh, G of ice is not stable because this is a GWV, water and vapor line, and at this point this is the where the G water line intersects. So GW is higher than that of, sorry, that is GI. GI is higher than of G water and G uh, vapor, right? So GI has a higher value. It means it has a lower stability. So it means that G of ice is not stable at that particular point. Hence, it shows the correspondence position between water and vapor at that particular point B. It is also known as the vaporization temperature or the boiling temperature, where ice is unstable, okay, and water and vapor is stable. It is the boiling point temperature or the vaporization temperature in chemistry or in thermodynamics, you can say. So this is how we use the GT diagrams in geological systems. And sometimes, let's say if you want to take this example also, so let's say there is a phase diagram like this, and if this is a rock and this is a melt, so sometimes at this particular point, let's say X, a particular rock Y plus Y melt can sometimes coexist at this point X, and this point will be act as a thermal buffer. So this is the reason. So from this diagram we can able to tell why melt act. So this is water, right? So water is in the conjunction between ice and vapor, but it is generally irrelevant to say that uh, that a rock has been vaporized. It is not possible to vapor a rock, but it is very unlikely to see, right? But water holds the system for natural water, for H2O. Water acts as a buffer for vapor and for ice. So from this we can able to infer if there is a two-phase system or three-phase system between a melt and a rock. So that is why we generally say that melt act as a thermal buffer in geological systems. So this is the reason. From the GT space diagram you can actually know the reason why we can call melt as a buffering thermal buffer in geological systems. So this is a very important point. Please do remember, the melt in a system generally act as a thermal buffer in geological systems. So, do you get it, guys? Hope it is clear.
Yes, sir.
Yes.
Yes, sir.
Yes. So these kind of statements are very important. Okay. So if you come up with this kind of statements, you can apply the knowledge of your thermodynamic systems or metamorphic or igneous systems what you are learned. So these are the very essential concepts. So please do try to remember these concepts. So this will be helpful for you, uh, your upcoming endeavors, right? So now, so this was the part. So now I will just show you there are the part that is left today is the mathematical parts for thermodynamics. So for this Gibbs free energy, so we know that this G is equals to H minus Ts. We are all familiar with this common equation. Okay. So and we also know this is valid at constant temperature and pressure, right? So yes. So we also know that this H enthalpy is, we can write this enthalpy in the form of energy plus work done. वही है ना enthalpy. So enthalpy क्या है? It is the summation of energy plus work done, right? And when you are saying energy, we are saying here internal energy, that is potential energy plus kinetic energy, right? Now what we know that from work done, W equals to F into S equals to F, मतलब क्या होता है तुम्हारा? F is your pressure into area and S is the distance, and area into distance means what? P into V. So W equals to P into V or PV, and H equals to E plus PV, we can write. Now if we differentiate this term PV, so delta of PV पार्शियल डेरिवेटिव करेंगे तो क्या होगा? P of dV plus V of dP. अगर तुम, if P is constant, if you are doing a derivative d of a constant term, it will be 0. So it will be P dV. Okay. So dW equals to minus P of dV. ये हम लोग जनरली लिखते हैं क्योंकि एक नेगेटिव साइन हम लोग देते हैं, क्योंकि with the this negative sign implies that when the volume decreases, हम लोग कब प्रेशर इंक्रीज करता है? when we are increasing the, if we are increasing the pressure, your volume decreases, it contracts. Okay. So so before that, I want you to be familiar with the partial derivative of like this term f of x comma z. So हम लोग ये ऐसा लिख सकते हैं dy equals to delta y of delta x when z is constant at dx plus delta y of delta z x constant at dz, right? So ये हम लोग partial derivative class में किए हैं. We have done this at our partial derivatives or mathematics class. We have done, everyone we have done this, right? So now delta y equals to del y by del x z dx plus del y by del z x dz, right? So what we know that entropy S is a function of temperature and pressure. So f of p comma t, it is a function of both pressure and temperature, right Monu?
Yes, sir.
So if we do integration on both sides, सो हम लोग एक बाउंड्री कंडीशन ले लेते हैं 298 केल्विन टेम्परेचर एंड 1 बार प्रेशर. दिस इज आवर इनिशियल एंड टी ऑफ पी हम लोग सही सरफेशियल कंडीशन हम लोग ले लिए. फॉर सरफेशियल कंडीशंस हम लोगों का टेम्परेचर 298 केल्विन और 1 बार प्रेशर में हम लोग रहता है. सो राइट. सो and for an upper limit let us consider T and P at any unknown temperature and at any unknown pressure, right? So ds equals to integration of 1 by P del S by del P dP plus integration of 298 of T del S by del T dt, क्योंकि हमारा टेम्परेचर 298 से T तक रेंज करता है और प्रेशर 1 से P. सो it is satisfying the pressure and temperature conditions. So we can also mix this upper and lower limits as we do in mathematics. So let name this term as A and let's name this term as B. ठीक है. So boundary conditions are 298, 1 and P and T. Okay. So if we uh, equate this term, it will be S P comma T minus S of 298 1 equals to A plus B. Now or S P comma T equals to S of 298 comma 1 plus A plus B. We will decipher the A and B term. So from this equation, I have just simplified this equation in general terms. So from this equation, we can say that if I know the entropy at any reference temperature and pressure, then we can calculate the particular value of it, right? Now हम लोग ने क्या देखा था, डेल एस बाई टी वी कैन राइट दिस. ये जो डेल एस जो टर्म है, डेल एस बाई डेल टी डी टी, और ये जो टर्म है, इस टर्म को हम लोग एक टर्म लिख सकते हैं. यू नो दैट वी कैन राइट दिस एज सी पी बाई टी डी टी. ये हम लोग ने पहले एकदम शुरुआत में देखा था, राइट?
यस सर, जो एज के बदले.
यस. सो इंटीग्रेशन 1 ऑफ पी एंड सी, ये जो ए टर्म है ना डेल एस बाई डी पी, ये जब हम लोग इसको तोड़ते हैं, मतलब व्हेन योर एंट्रोपी इज चेंजिंग विद रिस्पेक्ट टू प्रेशर. जब हम लोग प्रेशर के बारे में बात करते हैं, व्हेन यू आर टॉकिंग अबाउट प्रेशर, देन देयर इज अ वॉल्यूम चेंज, राइट? देयर इज अ चेंज इन वॉल्यूम. एंड वो वॉल्यूम कितना चेंज होता है, व्हाट इज द अमाउंट that our volume has changed, through which the volume has changed, we generally introduce a term called coefficient, right? So
यस सर.
it is related to thermal expansion. तो तुम्हारा जो volume is changing, the volume is expanding or decreasing, it is expansion due to thermal effects, right? So this is a thermal expansion, and in order to know or calculate that thermal expansion, we generally introduce a coefficient term, that is the alpha. Okay, so हम लोग generally देखते हैं alpha v. So v is your that volume part, and alpha is the, this alpha is the coefficient of thermal expansion. So generally हम लोग calculation का time ये we actually neglect this alpha term. So minus alpha v. So negative sign, you know what negative sign implies. So plus 298 t cp by t dt. Okay, cp by t dt. So this is our final expression, and we also know that volume is a function of both pressure and temperature. So dv equals to delta v by delta t at pressure constant dt plus delta v by delta p at temperature constant dp. So ये हम लोग लिख सकते हैं from the partial derivative, we know, right? So
यस सर.
तो इसी टर्म को, so dv by dt and dv by p को हम लोग जब लिखेंगे ना, so इसी टर्म को हम लोग जब लिखेंगे 298 of t, एक तुम्हारा अल्फा v dt आएगा माइनस एक कोफिशिएंट तुम्हारा v of change in V with respect to T एक आएगा and change in V with respect to P एक आएगा. So 1 by P beta V dP. So this is the term. जो अगर ये जो टर्म है इसको अगर हम लोग एक्सपेंड करेंगे और इफ इसको अगर इसको दोनों इफ वी जस्ट एक्सपेंड दैट टर्म इन टर्म्स ऑफ बोथ प्रेशर एंड टेम्परेचर इट विल लुक लाइक दिस एंड फाइनली इट विल लुक लाइक दिस क्योंकि दो टर्म के लिए दो कोफिशिएंट एक अल्फा एक बीटा अगर तीसरा आएगा तो यू कैन राइट इट एज गामा बट वी जनरली नेग्लेक्ट दिस टर्म for our mathematical for calculation or for empirically we generally neglect this term for to make the calculation easier, okay, and nothing else. To be precise you can calculate this but we generally neglect this and your vpt equals to v of 298 at your uh, standard temperature and your pressure is 1 bar now. So and please remember ये जो coefficients है these are for solid phases, okay, you cannot do this for liquid phases. So I think you know the reason why for solid phases, because when you are applying pressure to a solid it will contracts itself, right? So there will be reduction in volume but if you are applying pressure the amount of pressure which you are applying to a solid and the if the same amount of pressure if you are try to contract the liquid if so the liquid will try to just move from it, it will change its shape, right? So
Yes, sir.
so you cannot say so it will generally take the shape of the container in which it resides but solid में क्या होता है उसका तुम्हारा वॉल्यूम रिड्यूस हो जाता है but for water it will try to escape from that space, right? That is the
Yes,
difference.
sir.
So these coefficients of this thermal expansion term or generally liquid क्या होता है liquid vaporize कर जाता है but your solid can't vaporize at a single step. First it will have to convert it into liquid then the liquid can vaporize and it is only this option is not available for rock and melts. These options is available for ice water system vapor system, right? So this coefficient term you cannot use for a liquid phases, it have to be a solid pure phases term, right? So this is the difference. So 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 uh, so let's see a system. So this equation you can use to calculate your numerical. So now I will show you another. Let's take a reaction plus dd. Here a comma b comma c comma d are phases and small a small b small c and d are stoichiometric coefficients, right? So if we consume the del x, the change in x, so we can write, and so if you are calculating a del x of a reaction, so always remember the equation will be in the form of products minus reactants, right? So it will be c xc plus dx d minus, sorry, axa minus bxb. Now in this similar fashion if we want to calculate the change in, if it is change in x may be any term, okay, it can be your coefficient, it can be your mole, it can be anything, but for so it can also be g. So if you want to calculate the change in Gibbs free energy for a particular reaction you will just replace this x with g. So del g of a reaction will be c g capital C plus where C are the stoichiometric coefficients plus D G D minus A G A minus B G B. So now from this equation or formula you will be able to calculate the change in Gibbs free energy and you know how to calculate, that is it will be products minus reactants. This is the order now. So So from the first law of thermodynamic, what is the first law of thermodynamic states? So the first law of thermodynamics states
The energy neither be created nor be destroyed.
not be destroyed, right? So
Yes, sir.
if you want to derive G,
सर बस वो एक फॉर्म से दूसरे फॉर्म को ट्रांसफर होता है.
exactly. Now we already know the what is the first law of thermodynamics, right? Now the question is, if we want to derive the, the G, first law of thermodynamics from G, so we know that minus dE minus dW plus dQ equals to 0, because dQ equals to dE plus dW, ये टर्म हम लोग जानते हैं, right?
यस सर.
And Q is equivalent to H, and we also know that D of ST, thermal entropy, is greater than equal to dQy.
डीक्यूबीटी. यस सर.
So dQ equals to T ds
यस सर.
minus dE minus dW plus T ds will be greater than equals to 0, right?
यस यस सर.
Minus dE minus P dV plus T ds will be greater than equals to 0. So minus dE equals to d of PV.
सर आपने जो माइनस पीडीवी लिखा वो जो डी वाक्यम का थोड़ा सा चेंज होने के टर्म को यूज करके लिखा है ना जो माइनस पीडीवी जो थोड़ी बस कुछ मिनट के बाद में जो आपने निकाला था ना वही टर्म है ना. यस सर.
Yes. So uh, d of ts will also be 0. Now इसी इक्वेशंस को अगर हम लोग थोड़ा रीअरेंज कर देंगे, माइनस डी ऑफ ई माइनस पी डी वी प्लस टी डी एस, ठीक है, ग्रेटर देन इक्वल्स टू 0. सो अगर माइनस डी को हम लोग कॉमन ले लेते हैं, so what is E? Okay, so E will be, so when you are applying any pressure or due to that pressure, if your volume change is occurring, if it is W, so ये क्या होता है, E plus W हम लोगों का H हो जाता है, right?
यस सर.
And ये क्यों, TS D common, you have taken common of D, so the equation will becomes H of TS is greater than 0. so हम लोग ये देखो, और D यहाँ पे है डिफरेंशियल. So, okay, now, so Gibbs free energy is a work of both. It Gibbs free energy can be less than 0 and can be greater than 0. For a spontaneous reaction, del G is negative. Okay, and for non
यस सर.
spontaneous, G क्या होता है, पॉजिटिव होता है. So G equals to, हम लोग ये टर्म लिख सकते हैं, that H minus TS. So now you know the proof, how we can prove this from first law of thermodynamics, right?
यस सर. यस सर.
Yes. So minus d del g is greater than 0 and del g is less than 0 for spontaneous. Okay. And when d del g equals to 0 for equilibrium condition. So, so, so from this first, second, and third law of thermodynamics, and if we apply the same principle, okay, for rearrange करेंगे, we can see that at any space, at if we are referring to any space at particular temperature and pressure, that space can be defined by the uh, equation or defined by an expression of the uh, change in its entropy over the change in volume. So if any space actually defines the change in entropy with respect to the change in volume at a particular pressure temperature condition, we can call or the equation is given by the Clausius-Clapeyron's equation, right? So हम लोग उसके लिए expression क्या लिख सकते हैं? dp by dt equals to del s by del v, right? Over a space at particular pressure temperature, your the change of entropy with respect to the change in volume, right? So यही expression है Clausius-Clapeyron's का.
Yes, sir.
So this equation actually देखो, if you will see that these all these equations are governed by this thermodynamics of the metamorphic systems, or your of the inorganic systems, right? So you can actually define that your any reaction falling under this condition, you can or under the set of boundary condition, you can define the reactions with the help of thermodynamics in terms of entropy, gives free energy, and finally with respect to the term of del S and del V, change in entropy and change in volume change. Okay, so
जी सर। सर ये जो आपने अभी पढ़ा था जो एंट्रोपी वगैरह और थर्मोडायनामिक्स के लिए सर किस बुक को फॉलो करें, वो जेडी विंटर्स के हो गए या फिर कोई और बुक?
you can for the basic part you can read the JD Winter, and if you want to go in a little bit advanced, you can follow the Philpotts book. Philpotts, I have shared that book with all of you.
यस सर।
Philpotts, not each and every chapter. There is a chapter in Philpotts called thermodynamic systems. I don't exactly remember the chapter number, but you can follow that chapter, that thermodynamic chapter. You can follow to cover this thermodynamics part. बहुत अच्छे से explain किया हुआ है उस book में, Philpotts में. or what I can do is I will give you a supplementary note on thermodynamics. मेरे पास एक note है जो clear and concise लिखा है. You can so you are just you can follow the thermodynamics, right? What I have showed the derivation and concept, पूरा इसमें तो कोई दिक्कत नहीं है.
नहीं सर।
Okay, so the basic concepts of thermodynamics are clear from this class, and chemical thermodynamics I have in that class of chemical thermodynamics I have also showed the derivation of Gibbs Duhem and Gibbs free energy कैसे आता है, Gibbs Duhem का derivation जो है, I have shown the elementary concepts of thermodynamics, chemical thermodynamics in that class. If you will just look or take a glance at these two classes, you will just catch up to the mark. Okay, there will be no
यस
issues regarding thermodynamics. Okay.
यस सर। सर थोड़ा सा सर आपने सर ये थोड़ा मेरा दिक्कत हो रहा है कि सर आपने जो बीच में पूछा ना जो टेट्राहेड्रल साइड और ऑक्टाहेड्रल साइड, सर थोड़ा उसके बारे में थोड़ा एक एग्जांपल देके बता दें, इसमें थोड़ा बहुत दिक्कत हो रहा है।
कौन सा रिपीट करो
सर
थोड़ा.
अभी आपने जो के क्रिस्टल के बारे में पूछा था, इसमें से कितने टेट्राहेड्रल साइड है, कितने ऑक्टाहेड्रल साइड आते हैं मिनरल पे, सर वही थोड़ा एक एग्जांपल देके सर मुझे समझा देने के बहुत दिक्कत कर रहा है बीच बीच में।
ओके ओके ओके, अच्छा मतलब तुम अगर ये KAl SI3 जब ले रहे हो, ओके, सो इन 1 second. 1 second. Where is my- हाँ, yes, हेलो,
यस सर।
यस. सो ये जो KAl SI3O8 जो था, सो यहाँ पे तुम लोगों का डाउट था कौन सा ऑक्टाहेड्रल और कौन सा टेट्राहेड्रल साइड में जाएगा, राइट?
यस सर, यस सर, यस सर।
ओके, तो देखो जनरली ये तुम्हारा जो सिलिकॉन जो है, ठीक है, सो एल्यूमिनियम का तुम्हारा 3+ होता है, सिलिकॉन का 4+ होता है, राइट? सो अगर तुम इसका मतलब स्टेबल कॉन्फ़िगरेशनल स्ट्रक्चर देखोगे KAL-SI308 का, ओके, सो यहाँ से तुमको पता चलेगा कि यहाँ पे तुम्हारा जो सिलिक मतलब जो टेट्राहेड्रल साइट होता है सिलिकॉन KAL-SI308 का, तो इसके लिए तुमको XRF स्टडी या फिर जो बैक स्कैटर डिफ्रेक्शन इमेजिंग करना होगा, ठीक है। तो तुमको ये एक्चुअली देखने के लिए जे एग्जैक्टली कितना साइट्स प्रेजेंट होता है पोटाश फील्ड्स पर, बट potash feldspar generally contain your 4 tetrahedral sites, ठीक है। क्यों 4 tetrahedral sites, क्योंकि यहाँ पे जो तुम्हारा बेसिकली, बट टेल मी वन थिंग दैट ये दिस इज अ सीड सिलिकेट, राइट?
सर ऑफिसर फर्स्ट पार्ट में तो वो टेक्निकल स्टडीज होते हैं।
सॉरी सॉरी सॉरी, इट्स अ टेक्टोसिलिकेट, राइट? जैसे कि
यस सर, यस सर।
यस, इट्स अ टेक्टोसिलिकेट। सो इफ इट इज अ टेक्टोसिलिकेट मतलब, so quartz is your टेक्टोसिलिकेट, राइट?
यस सर।
सो टेक्टोसिलिकेट में तुम्हारा सिलिकॉन इस टू ऑक्सीजन रेशियो कितना होता है?
सर 1:2।
हाँ,
सर 1:2 होता है ऐसा ही।
एग्जैक्टली। सो सिलिकॉन इज टू ऑक्सीजन रेशियो इज 1:2, राइट? लेकिन देखो इन केस ऑफ, सो पोटाश फील्ड्स पर तुम्हारा टेक्टोसिलिकेट है,
यस सर।
तो इसका जो कॉन्फ़िगरेशन है, इसका कॉन्फ़िगरेशन ऐसा होता है।
यस सर।
तो लेकिन तुम इसका केमिकल फॉर्मूला से देखो, के है, Al है, Si3O8 है। अगर तुम यहाँ पे सिलिकॉन इस टू ऑक्सीजन रेशियो करोगे, सो Si3 और O8 हो रहा है, तो 3:8। सो अगर तुम 3:8 फ्रैक्शनेट करोगे तुम्हारा कितना आएगा? तुम अगर 3 डिवाइड बाय करोगे, इट इज कमिंग 0.375, राइट? बट तुम्हारा होना चाहिए
यस
1:2, मतलब 0.5 होना चाहिए। तो
सर।
इसका जो स्टेबल मतलब जो स्टेबल कॉन्फ़िगरेशन है ये इसको फॉलो नहीं कर पा रहा है, ठीक है। ये और क्या होता है, इसका जो नियरेस्ट नेबर है वो एल्यूमिनियम है, मतलब एल्यूमिनियम क्या कर सकता है, इन प्लेस ऑफ सिलिकॉन एल्यूमिनियम तुम्हारा सिलिकॉन के साइड में जा सकता है, ठीक है, क्योंकि यहाँ का चार्ज डिफरेंस इज ओनली 3+ एंड 4+, मतलब चार्ज डिफरेंस इज ओनली +1 यूनिट का चार्ज डिफरेंस है, राइट?
यस सर।
और रेडियस इसका तुम्हारा मतलब मोरलेस 20% से ज्यादा नहीं है, इट इज बिलो 20 and 15%, ओके। सो एल्यूमिनियम कैन गो इनटू द साइट ऑफ टेट्राहेड्रल साइट, और इसको और
सर वो जो सॉलिड सॉल्यूशन के बीच में से जो रूल होता है वो है ना जो क्रोमोफ्लेग एडमिटेंस।
एग्जैक्टली। सो
सर
देखो,
ये सर अभी।
सो अभी तो क्या होगा, तो ये जो एल्यूमिनियम है, और अगर ये Si3O8 मतलब ये अगर उसका जो जनरल फॉर्मूला है टेक्टोसिलिकेट का, उसको उसका जो सिलिकॉन इज टू ऑक्सीजन रेशियो है, द सिलिकॉन इज टू ऑक्सीजन रेशियो ऑफ टेक्टोसिलिकेट इज 1:2। इफ इट कैनॉट मेंटेन इट्स स्टेबल कॉन्फ़िगरेशन, देन इट विल नॉट बी एबल टू फॉर्म अ टेक्टोसिलिकेट, राइट?
यस सर।
So its configuration is such that the aluminum jumps into the tetrahedral site, क्योंकि Si3O8 है, ओके। और टेक्टोसिलिकेट में तुम्हारा ये जो मतलब इसका जो स्टेबल कॉन्फ़िगरेशन है, इस पे अगर तुम्हारा ये 4 टेट्राहेड्रल साइट रहेंगे, ओके, एंड to maintain this 4 tetrahedral side, that aluminum jumps to Si, into the Si side, so Al Si3, so 3 plus 1 4, okay, to maintain the 1:2 silicon is to oxygen ratio। ये
यस सर।
टेक्टोसिलिकेट का कॉन्फ़िगरेशन को कंप्लीट करने के लिए ये तुम्हारा 4 tetrahedral site will be present in case of KL-Si3O।
सर थोड़ा इसके बारे में बताइए सर, जैसे कि जो जाम और गेट में जो क्वेश्चन आता है कि इसमें से कौन सा एलिमेंट ऑक्टाहेड्रल साइड पे है या फिर कौन सा एलिमेंट टेट्राहेड्रल साइड पे है, सर इसको कैसे डिटरमाइन करेंगे? सर आपने अभी जो
ओके ओके, ये देखो ये केमिकल की रेडियस रेशियो का प्रिंसिपल में होता है, जैसे कि तुम्हारा ये मैं तुमको और एक एग्जांपल देता हूँ। अगर तुम लेट्स से ये लेते हो, गार्नेट का जनरल फॉर्मूला ले लो। लेट्स टेक द जनरल फॉर्मूला ऑफ गार्नेट। तो X3 Y2 Si3O12, राइट?
Yes, sir.
तुम एक चीज देखो, Si3O12, ये जो SI है, और ये जो, सॉरी तुम ये नहीं, ये थोड़ा कम, ठीक है मैं ये भी बता रहा हूँ। तुम Mg2SiO4, तो Mg2SiO4 में, या फिर हाँ, तो तुम ये बोल सकते हो कि Mg2SiO4 में जो ओलिविन का जो स्ट्रक्चर है, वो Mg2 कौन सा साइड में क्रिस्टलाइज कर, Mg कहाँ पे घुसेगा? टेट्राहेड्रल में घुसेगा या फिर ऑक्टाहेड्रल में घुसेगा?
सर वो ऑक्टाहेड्रल को किसी
क्यों?
सर ये जो आपने अभी जो बोला ना एसआई और ऑक्सीजन के रेशियो में बेस करके हम जो सिलिकेट के बेसिस पे कर रहे हैं जो 1:4 हो रहा है, तो फिर एमजी जो सामने रख रहा है वो ऑक्टाहेड्रल साइड पे रुकेगा सर।
हम्म, ओके, ठीक है। तो तुम मुझे एक चीज बताओ, ये ओलिविन का जो ऑक्टाहेड्रल साइट है, हाउ मेनी ऑक्टाहेड्रल साइट्स ऑफ ओलिविन आर देयर?
सर टू।
हाउ मेनी ऑक्टाहेड्रल साइट्स इन ओलिविन आर देयर?
सर टू हो गया जो मैग्नीशियम 2 है इसकी
यहाँ
वजह
पे M1 और M2 दोनों ऑक्टाहेड्रल साइट है, ठीक है। M1 साइट में क्या होता है, M1 साइट में जो तुम्हारा M1 साइट है, ये तुम्हारा थोड़ा डिस्टॉर्टेड है, थोड़ा सा छोटा है, और M2 साइट इज योर रेगुलर ऑक्टाहेड्रल, ठीक है। तो क्या होता है, Mg2SiO4 में जो कुछ मैग्नीशियम M1 साइट्स में जाते हैं और कुछ मैग्नीशियम M2 साइट्स में जाते हैं, फाइन।
जी
सपोज
सर।
Mg2SiO4 एंड, और एक क्या है, Fe2SiO4, फ्रॉस्टेराइट एंड फायरलाइट, राइट?
जी सर।
सो Mg, Fe hold to SiO4, ठीक है। सो कभी कभी ओलिविन में क्या होता है, कुछ एक्स्ट्रा एक्सट्रेनियस एलिमेंट्स आ जाते हैं। मतलब एक्सट्रेनियस एलिमेंट्स मतलब ओलिविन के साथ कभी कभी तुम्हारा, लेट सपोज टाइटेनियम और कुछ अलग मिनरल जैसे कि सरपेंटिन तुम्हारा हो जाता है, ठीक है, ड्यू टू अल्टरेशन। तो वो जो एलिमेंट्स आता है ना, तो वो एलिमेंट्स तुम्हारा कुछ M1 और M2 साइड्स में घुसने का कोशिश करता है। जो बड़ा साइड्स होता है वो कभी कभी थोड़ा लार्जर कैटायंस को एकोमोडेट करता है, ठीक है। सो समटाइम्स इन केस ऑफ ओलिविन, इन the M1 and M2 sites there may be different elements, और मैं जो तुमको बता रहा था X3Y2 Si3O12। सो तुम मुझे ये बताओ कि X3 और Y2 साइट क्या क्या है गार्नेट में?
सर वो X3 ऑक्टाहेड्रल साइड पे है और Y2 टेट्राहेड्रल।
X3,
हेलो।
okay, you are telling me that that X3 is your octahedral
ऑक्टाहेड्रल।
site and Y2 is the tetrahedral site. तो H3 क्या है?
सर X3 वो एलिमेंट है जिसका वैलेंसी 2+ होगा।
X3
सर X3 पे वही एलिमेंट रहेगा ना जिसका वैलेंसी 2+ होगा।
और Y2 में?
सर वो एलिमेंट रहेगा जिसका वैलेंसी +3 होगा।
तुम श्योर?
ये सर आपने जो बेस पे लिखा है ना X3 तब आएगा जिस सर हम जो अगर एल्यूमिनियम ऑक्साइड के फार्मूला देखेंगे तो फिर Al2O3
ओके
जो होता है,
ओके ओके।
सर उसमें से एल्यूमिनियम का +3 होता है वैलेंसी और ऑक्सीजन पे -2 होता है। सर अभी तो आपने ये लिखा है ना X3Y2,
यस,
तो फिर Y का वैलेंसी।
लेकिन तुम मुझे एक चीज बताओ, गार्नेट में Ca रहता है, राइट?
ये सर।
सो Ca का ऑक्सीडेशन स्टेट क्या होता है?
सर +2 होता है।
ओके, लेकिन तुम्हारा Ca क्या हमेशा ऑक्टाहेड्रल साइड में जाता है?
नहीं सर।
हम्म।
नहीं सर।
तो Ca तुम्हारा कभी कभी तुम्हारा क्यूबिक साइड में भी जा सकता है ना।
यस सर।
सो इसीलिए जो H3 जो साइड है ना, इट कैन होल्ड बोथ योर ऑक्टाहेड्रल एंड क्यूबिक कोऑर्डिनेशन एंटिटी, राइट। और
यस
Y2
सर।
जो है ये सिर्फ ऑक्टाहेड्रल को एकोमोडेट करेगा। आप समझ में आया।
और सर ये सर, ये सर, सर वो जो SI3O12 लिखा है वही पार्ट टेट्राहेड्रल होगा क्या?
कौन सा।
सर आपने, सर ये समझ आ गया कि क्यूबिक क्या हुआ और ऑक्टाहेड्रल। सर इसमें टेट्राहेड्रल साइड में कोई कुछ नहीं है?
SI3 है टेट्राहेड्रल।
ये सर, ये सर, ये सर।
दिस वन इज योर टेट्राहेड्रल साइड। लेकिन ये गार्नेट में और एक चीज होता है, जैसे कि ये अगर तुम लोग अगर ये स्ट्रक्चर पढ़ना चाहते हो तो मैं एक क्लास ये तुम्हारा पूरा सिलिकेट स्ट्रक्चर का कौन सा क्या एलिमेंट मतलब कौन सा क्या साइड में आता है, मैं तुमको ये डिटेल में पढ़ा दूंगा तुम लोगों को। तो और एक चीज जो मैं गार्नेट के बारे में बताना चाहता हूँ, गार्नेट में ये जो तुम SI3 देख रहे हो ना, मतलब गार्नेट के लिए 3 ही टेट्राहेड्रल साइड एकोमोडेटेड है, ओके। और यहाँ पे जो अगर जो एल्यूमिनियम जो रहता है गार्नेट में वो जनरली तुम्हारा ऑक्टाहेड्रल में घुसता है, राइट।
ये सर।
लेकिन कभी कभी गार्नेट में इट इट कैन हैव एक्सेस ऑफ SI3 प्लस, मतलब SI 3 से ज्यादा रह सकते हैं गार्नेट में। उन सब गार्नेट को मेजोराइट गार्नेट कहते हैं, और वो बहुत ही इन डेप्थ मतलब हायर प्रेशर
ये सर,
टेम्परेचर कंडीशंस में मिलते हैं, दैट इज कॉल्ड
ये
मेजोराइट
सर
गार्नेट।
आपने एक बार बोला मुझे ग्रेटर डेप्थ का हायर जोन पे।
यस, मेजोराइट गार्नेट। तो ये एक्चुअली तो ये चीज तो तुम लोगों को कवर करने के लिए तुम लोगों को पूरा एकदम क्रिस्टल स्ट्रक्चर थोड़ा डिटेल में पढ़ना होगा। सो आई थिंक इन नेक्स्ट एक क्लास में तुम लोगों को ये पूरा स्ट्रक्चर मतलब पूरा कॉन्फ़िगरेशन पूरा डिटेल में थोड़ा बता देंगे, ठीक है। फॉर
ये सर,
पायरोक्सी
सर
एंड
उस,
हाँ बोलो।
सर आपने अभी जो बोला ना तो जो क्रिस्टल के स्ट्रक्चर को सर कौन सी बुक फॉलो करे तो फिर अच्छा रहेगा, वर्किंग है फिर?
देखो ये तुम्हारा एक्चुअली मतलब तुम पार्किंस फॉलो कर सकते हो, या फिर वो नेसे नेसे भी ठीक है बेसिक के लिए। और एक है तुम क्लाइन हल्बर्ट का एक बुक है, यू कैन फॉलो दैट बुक। क्लाइन हल्बर्ट है तुम लोगों के पास।
नहीं सर, मेरे पास मेसे और वर्किंग है।
तो ठीक है, मैं तुम एक काम करूंगा, मैं मिनरलॉजी के लिए तुमको तुम लोगों को सप्लीमेंट के लिए क्लाइन हल्बर्ट दे दूंगा। और बेसिक और एक तुम्हारा जो एक्चुअली क्वेश्चन है ना, जो मतलब तुम्हारा जो तुम जो मतलब क्यू S13 में मतलब ये चार्ट्स टेबल बनाने के लिए Q3 Q4 होता है, मतलब जो XRD से जो स्ट्रक्चर एकदम पूरा देखा गया है, जो मतलब एग्जैक्टली क्रिस्टल स्ट्रक्चर जो टेट्राहेड्रल ऑक्टाहेड्रल साइड्स है M1 M2 M3 M4 साइड। जैसे कि अगर तुम पायरोक्सिन और एम्फिबोल ले लोगे तो एम्फीबोल में तुम्हारा M1 M2 M3 साइड्स रहता है, राइट, डब्ल्यू साइड रहता है। क्योंकि अगर तुम
ये सर।
एम्फीबोल लोगे तो उसका जो जनरल फॉर्मूला है W0 to 1 X2 Y5 Z8 O22 दिस इज योर जनरल फॉर्मूला फॉर एम्फीबोल, राइट।
ये सर।
सो यहाँ पे M1 M2 M3 ये ए ये सब कोऑर्डिनेशन साइड रहते हैं, मतलब ऑक्टाहेड्रल के ही अंदर तुम्हारा M1 M2 M3 और ये सब मतलब पार्टीशंस रहता है, ठीक है। तो OH एक तुम्हारा फंक्शनल ग्रुप हो गया, ये एक अलग साइड में जाता है। तो इनके लिए तुमको डिटेल्ड स्ट्रक्चर मतलब अभी तुमको मैं इधर बताऊंगा फिर भी तुमको मतलब यू कैन नॉट कोरिलेट, मतलब इसको तुमको डायग्राम
सर,
दिखा के समझाना पड़ेगा। सो और एक
ये
हाँ बोलो बोलो, एक बुक है जो
सर,
एक हाँ बोलो।
सर मैं तो बोला हूँ, सर अगर आप ये जो आ रहा है इस सैटरडे को, अगर आप ये कोऑर्डिनेशन नंबर और इस जो टेट्राहेड्रल ऑक्टाहेड्रल वो जो सिलिकॉन स्ट्रक्चर के ऊपर सर क्लास ले
ओके
जाते तो
ओके, देखो मैं देखो ये जो सिलिकेट स्ट्रक्चर का जो क्लास है ना, तो ये तुम्हारा ये पूरा स्ट्रक्चर तुमको पूरा एकदम PPT बना के तुम लोगों को समझाना पड़ेगा। तो इस सैटरडे अगर मैं कोशिश करता हूँ इस सैटरडे तुम लोगों को ये अगर ये पूरा पूरा कवर कर सकूँ, नहीं तो मैं आई विल टेक 1 वीक मोर टाइम, नहीं तो इस सैटरडे या फिर नेक्स्ट सैटरडे श्योर तुम लोगों को ये पूरा सिलिकेट स्ट्रक्चर कवर करवा दूंगा, ठीक है।
सर। सर सर इसी सैटरडे को हो जाएगा तो सर
तुम
थोड़ा
लोग
ध्यान।
तुम लोग
सर अगले वीक पे सर हमारा जो व्हाट्सएप है तो डिपार्टमेंट में
ओके ओके
सैटरडे।
ओके ओके, आई एम ट्राइंग टू कवर दिस सैटरडे। अगर इस सैटरडे क्योंकि ये देखो पूरा बहुत ही वास्ट स्ट्रक्चर है, मतलब तुम लोगों को स्पिनल स्ट्रक्चर और क्योंकि पूरा ये पायरोक्सिन एम्फीबोल पूरा डिटेल्ड में थोड़ा समझाना होगा, अगर ये समझाना होगा तो एकदम पूरा तो इस सैटरडे अगर 2 घंटे में पूरा नहीं भी होता है तो नेक्स्ट सैटरडे, या फिर क्योंकि अभी भी तो क्लास है, 5-6 क्लासेस है, तो या फिर नेक्स्ट टू नेक्स्ट सैटरडे पूरा पूरा टोटल कवरेज कर देंगे, ठीक है? इट विल बी ओके आई थिंक।
यस सर।
ओके, सो
यस सर।
इस सैटरडे स्टार्ट कर देंगे। सो जितना हो
यस
सके
सर।
पूरा डिटेल में बता देंगे, क्योंकि दीज आर इम्पोर्टेंट, क्योंकि ये तुम अगर स्ट्रक्चर, इफ यू कैन स्टडी दिस स्ट्रक्चर्स, तुम लोगों के पास एक आइडिया हो जाएगा हाउ टू, मतलब कैसे, कौन सा एलिमेंट, कौन सा मिनरल कहाँ पे, मतलब कौन से टेक्टोनिक सेटिंग में फॉर्म करता है, सबडक्शन की वजह से उनके जो स्ट्रक्चरल साइट्स है, हाई टेम्परेचर की वजह से उनका जो स्ट्रक्चरल साइट है कैसे चेंजेस होता है, ठीक है? मोनोक्लिनिक ट्राइक्लिनिक के बारे में जो ट्रांजिशन जो होता है साइट्स में, कैसे वो, मतलब प्रेशर के साथ फेस ट्रांजिशन होता है, तुम लोगों के पास एक पूरा ब्रॉड आइडिया है। ओके, आई विल कवर दिस पार्ट। ओके, ओके, सो वी आर एंडिंग दिस क्लास टुडे। ओके,
यस सर।
ओके।
सर आपने जो आपको जो सर जो मेल कर दिया था आपने,
हाँ, ये
वो सर जो
दैट
असाइनमेंट टाइप की।
दैट मेल, वो मेल एक्चुअली मेरा तबीयत ठीक नहीं था तो मैं फॉरवर्ड नहीं किया था। मैं ये फॉरवर्ड कर दूंगा आज, ठीक है?
जी सर।
ओके।